hard at all, but a lot of little bit notes here for you all. You did this last year. A function is continuous at a point C if the following three things are true. These are the three things that you should remember, I hope, from last year. If you don't, it's all right. You'll know it.
Was it during the online?
Was it during the online? No, it was actually off. So f of c has to be defined. So to be continuous, the first thing you need to do, we talked about it last year, is called you plug it in, and you have to get out an answer. So meaning you can't have 0 in the bottom. That would not be defined. And you cannot have like a square root of a negative. That would also not be defined. Every other time it's pretty much defined that I can think of. Number 2, you have to take the limit of the function. And last year is when you first learned about this, but you had no idea what limits really were. You take the limit of the function, and so from both sides, it has to exist. So that's the other thing. So at this point C, you have to be able to take the limit and get an answer out. Like, oh, it approaches 5 from the left. Oh, it approaches 5 from the right. Step number 3 pretty much is saying then that these two have to be the same. So like when you plug it in and you get 5, and then you take the limit and you get 5, then it's continuous. So the limit as x approaches c of f of x has to equal whatever you get when you plug it in. These are the 3 rules. Now for all of them, you're not going to have to do these 3 rules. For a few of them, you will. I'll show you some examples in a minute. Before we get going on the continuity, every year the students get this wrong, so I want to go over this with you. Limits, write this out in the corner somewhere. Those are y values that you approach. Limits are the y values that you approach. Like as x goes to 2, what y value are you approaching? Oh, I'm approaching 5. Oh, I'm approaching, okay, what y value? Continuity, though, which we're about to talk about, continuity, is over a domain, usually in an interval form. Domain meaning your x's, okay? Why do they do this? I hate that they put both of these in the same section, but it's because of this second part here where it says limits. But just so you know, limits are y values. Continuity is on a domain, which means over the x, okay? Somehow magically get that in your head. And that will definitely help you out come the lovely test. All right, a polynomial and a rational function. So polynomial and a rational function is continuous everywhere in their domain. A polynomial is continuous everywhere in its domain, and a rational function. So what do I mean? Remember, continuity is just like, where do I not have to lift up my pen or pencil? In your remembrance of pictures of polynomials, of any kind of picture I've given you, where is their problems at? What is that called? Do you remember? Holes. Where else? It's my favorite word, y'all. Mother functions. Asymptotes. Okay? So problems occur at holes, at jumps, at asymptotes. That's what you're going to look for in the homework tonight. Figure out where the problems are at. Where's the hole at? Where's the asymptote at? Where's the jump at? That's where the problem will be, and then you just state the continuity of it. Okay? So now we're going to do some examples, and I'm going to write them all out. So give me 1 minute. State the continuity in interval notation. So f of x equals x squared minus 2x plus 3. So here's some examples of what you've been doing tonight. It's really quite algebraic and it's nothing too difficult to be familiar with. All right, so look at this one right here, x squared minus 2x plus 3. Where's that continuous?
Everywhere.
Everywhere. It's a polynomial. What about x cubed minus x? Everywhere. So how do I write it? Any polynomials, they're continuous everywhere. So they're continuous along their domain, which would be negative infinity to infinity. Polynomials, their domain of a quadratic of a parabola is from negative infinity to infinity. Same thing with the cube, negative infinity to infinity. So there's its continuity. Easy. Let's look at this one. This is a rational function, meaning a fraction. Where does it have a problem area? Where would that be a problem area? At only 0, correct? 0 would be the asymptote. So you would say, okay, Mrs. Seta, it's continuous from negative infinity up until 0. And then we have this asymptote, and then you say united with 0 to infinity. So I'm good from negative infinity to 0, and then I'm good from 0 to infinity. But at 0, there's an asymptote, and that would be the continuity. Done. Okay? What about this one? 1 is a problem area, but is it a whole? Is it an asymptote? What is it? So if you don't remember this from last year, I'll refresh you real quick. If you factor the top, what does the top factor into? Okay. If it cancels, it's a whole. Cancels is a whole. So, and you actually say at x equal to, you like almost set this equal to 0, you change the sign. So 1. So 1, there's a whole. If you were to graph this, guys, and you can always graph if you're good at graphing and looking at it visually, this is actually going to look like a straight line. But at the point 1, there's going to be a hole in the graph that you won't see unless you look at the table. The table will say error at 1. So that's why it's good to know your algebra and cross it off. So what would be the continuity then? What would you say? From negative infinity to 1, united with 1 to infinity. Okay, so there's my problems. All right, here we go. 2 here. When is this going to be a problem? When would the bottom ever become 0 there? At what? At I. Is there I's on your coordinate grid? No. There was tons of them on the SAT, ACTs.
There's tons of them. There's like 5 or 6 problems. No, I didn't know how to get any. Yeah, there wasn't any on the SAT.
This will never become 0. Ever. There is no value for x that, I mean, if you put 0 here, you'd still get 1 in the bottom. If you put -1 there and square it, you'd get 2. There is no value that will ever make it 0. And again, you can look at this in the graphing calculator, but it is continuous the whole time. There's not a problem. So you want to be careful about that. All right, last one here, number 6. Again, +2 minus 2 is what it factors. If it cancels, it's a whole. So there's a whole at x equal to -2. But what is that if it's left in the denominator? That is an asymptote. There's an asymptote at +2. So we have 2 areas that are problem here. We have a whole at -2. We have an asymptote at 2. So then how do I write the continuity? Well, you would say, I'm continuous from negative infinity up until the first lowest number. What's the first lowest number? -2, united with -2 to 2, united with 2 to infinity. That is the continuity in interval notation. Okay. Now, of course, you're going to have like ease on homework tonight. Just again, set the bottom equal to 0. If it's a rational fraction, if it's a polynomial, it's never going to be. It's going to be infinite. Okay. But most of the time, bottom equals 0. All right. Now let's just kind of go over this discontinuity again. Discontinuities. So from pre-calc to calc, we change words. I don't know why, it annoys me, but it is what it is. Instead of saying whole, which we were learning last year all the time, or point discontinuity, we now use this phrase, removable discontinuity. Okay? Instead of saying asymptote, that we were saying all the time last year, we now use the phrase non-removable discontinuity. Why do they do that? I don't know. I didn't make up the math. I just tell you the math. It's just what they do now. So they're going to ask you, they're like, state the removable or the non-removable discontinuity. All they're asking you is state where the whole is or where the asymptote is. That's it. Okay. So don't freak out when you see these words. That's all it'll mean. So for example, state the type of discontinuity. And they'll give you a function x minus 4 over 2x squared minus 5x minus 12. Y'all, I'm serious. I need to get rid of this, but y'all should know how to factor, and I'm thankful that Metrolina, we know how to factor here. Do we know how to factor this one? I pray y'all know how to. Bottoms up. That's exactly right, okay? Thank God for Miss Davis. I was trying to say this to my SBCC students. I'm like, and then you bottom it up. And I'm like, they don't know her at all, poor people. So let's see, what multiplies to a negative 24 but adds to the middle, which is negative 5? What two numbers multiply to negative 24 but add to negative 5? 8n3, negative and positive, x. Because there's a number in front, divide by 2, divide by 2. If it reduces, reduce it, so x minus 4. If not, bottom up. So if you cancel, you are a whole. So you have a whole or a removable discontinuity at x equal to, change the sign, 4. That's what you would say. This one is in the bottom, right? If it's still in the bottom, then it's a what? It's an asymptote, which is non-removable discontinuity at x equal to, set that equal to 0, negative 3/2. So that's the other part that it'll ask you in directions for homework tonight. That'll say, tell me what discontinuity it has. Okay, removable, whole, non-removable, asymptote. All right, then just some other type of discontinuities here. You have what's called a one-sided continuity. Let me give you an example of that one. F of x equals the square root of 3 minus x is continuous where? And then I'll do another one in a minute. And we're actually almost done. What are you not allowed to be underneath a square root? Negative. Can you be 0? You can be 0 if you're not in the denominator. If you're in a denominator, you can't be 0 because that's just a given. So I'm going to show you 2 ways to do this. If you were to put this in your calculator, because some of you are more graphically inclined than I am, but you can put it in your calculator. You can look at this. This would be shifted over and pointing that way. Remember, right? Square roots go like that. Okay. So some of you would be right now able to look at this and be like, oh, what's the domain? Where's it continuous? From where to where right now? Negative infinity up to 3. Okay. Some of you are more probably like me where you're like, I like the algebra, Mrs. Seta. So what you would say was be under here, 3 minus x has to be greater than or equal to 0 because it's not allowed to be a negative. And then you just be like, okay, 3 has to be greater than x. Let me write it the other way. X is less than or equal to 3, or from negative infinity to 3 with a bracket. Okay, with a bracket because you can equal 0. So there's 2 ways of doing it. Again, some of you like the graph and totally allowed to do that. Go in your calculator, draw it for me, prove it to me by a drawing, something like that. and then write your continuity. It's continuous along its domain. So there's one-sided. You can also be continuous over a closed interval. And I want to give you an example of that one. Square root of 9 minus x squared is continuous. Where? Again, this one, I would shockingly enough do this graphically. And I'll show you why algebraically it would be annoying to you in a moment. So just so you see what this looks like if you were to graph this, this is half of a semicircle. This is half of a circle. It would go radius of 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and it goes like that. And then if I graph the negative of this, that would be the bottom half of this circle. But right now, where am I continuous? From where to where? From -3 to 3, and you put it in brackets. If I were to do this algebraically, like I just showed you on the one above, I would still go like this. I'd say, okay, 9 minus x squared is greater than or equal to 0. And then you FOIL it. And I don't think I remember last year you did not like these. Do you remember doing with inequalities what's called the sign test? So you would have -3, 3, you would have, my SPCC students are doing this all the stinking time. You'd have 3 zones. You have to pick a number in here, plug it in here, see if it's true or false. And actually the only one that's true is right here. So that's why I'm saying, yeah, I don't want to do it algebraically, but for those of you who like it that way and remember that, because that's the hardest part is remembering. For this one, it's better graphically, way better. All right. Last but not least, we're going to do piecewise function continuity, and then just 2 examples of that. And then I'm going to do one of your homework problems right now. Actually, I take that back. I'm doing 2 of them. You're welcome. That means you have 12? How embarrassing. It's embarrassing for my people. All right, continuity of good old piecewise. And ask you if it's continuous at a particular point. You have to do the 3 parts of the continuity definition. So again, back to this right here, where I wrote a function is continuous at a point C if the 3 things exist, if you plug it in and you get a value, if the limit exists from both sides, and if those 2 numbers are the same. You have to do all 3 of those. So we're going to do that right now. So step number 1, you have to plug it in. If you want to write yourself little notes, plug it in. Is the f, what does the f of 1? Number 2, now you look at the limits from both sides. So does the limit as x goes to 0, again, remember that's your c. Does the limit of the function exist from both sides? So where would you plug 0 in if you're finding it from both sides, the top or the bottom now? Well, the top really, because this equals 0. This, when it says does not equal 0, then you just keep it going from here. But you should all know this one. What is this one? What's the 1? We know that one. The limit as x goes to 0 of that guy is 1. Wait a second. So if I plug it in and I get out a 1, and the limit from both sides is 1, then what is step 3? They're the same. It's continuous because they're the same. I should say they're the same. Then all you would say is, yes, it is continuous at x equals 0. Boom. Okay? So you have to prove 3 points. We did this last year. We called it justification. You took a quiz on it. You hated it, but it was torture. I want to show you one that works, but I want to show you one that doesn't work because I think you need to understand they're not all going to work. So let's do it for this one. So step number 1, plug it in. That's my C. My C is 3. So f of 3, would you plug it into the top or into the bottom piece? The top. So -3 squared plus 4. Do I square that negative? Yes or no? No. The negative is not in parentheses. So this is actually equal to -5. Right? Number 2, now you take the limit from both sides. Remember, that's what limit means. X approaching 3 from the right, and the limit as x approaches 3 from the left of the function. So if I approach it from the right, would I go to the top piece or the bottom piece if I'm coming from the right? The bottom. So 4 times 3 minus 8 is 4. From the left, we already figured that one out. It's -5. Are those the same? No, I don't have a limit then, is what that means. So there's no limit, or, good old D&E. If that's the case, then it is not continuous at x equal to 3. Not continuous at x equal to 3. All right, and I'm going to do 2 problems for you because the children in the other class didn't like the trig so much, and I figured why not save you the hassle because I'm just that nice of a person. All right, so let's continuous. Where is it? You don't have to write this down, discontinuous, but that's what the question is asking. Where is their problem areas? So if you want to graph this tan of 2x, and I hate that they gave you tan of 2x because that's like the one graph we don't do a lot of. We do a lot of the sine and a lot of the cosine, but of course they did tan. So if you remember good old tan of theta and what it looks like, and if you don't, write it down. That's why I'm doing it. So tan of theta goes like this. It has an asymptote right here at pi over 2. And it does a little curve like that. And then it has another asymptote right here at 3 pi over 2. And then it just keeps going, right? Well, if I'm letting my theta be 2x, right? Theta is 2x. And I know there's an asymptote at pi over 2 and 3 pi over 2. So you say, okay, 2x equals pi over 2, because that's where there's an asymptote. And you solve it for x. Divide by 2, divide by 2. What's pi over 2 divided by 2? Anybody know? Pi over 4. There's the one problem area. Now you let 2x equal 3 pi over 2. Divide by 2, divide by 2. X equals 3 pi over 4. Guess what's going to keep happening, y'all? Because these are not the only 2 asymptotes. The graph of tangent looks like that. It just keeps making all these little like almost cubics all the way. And it keeps going. So x is you have non-removable discontinuities at pi over 4, 3 pi over 4, 5 pi over 4. Where else, y'all? Set, right? It just keeps going on and on and on and on. So the way the back of the book does it, they do this K stuff, which I did one time with you last year. I remember y'all hated it. But the back of the book says when x equals 2k plus 1 times pi over 4, for k equal to 0 plus or minus 1 plus or minus 2, on and on and on. And I'm like, oh my gosh, just write this. They're non-removables at the pi over 4, the 3 pi over 4, the 5 pi over 4, et cetera, et cetera. And obviously plus or minus because you could go to the other side. But I hate that they gave you that tangent, so that's why I did you that one. I'm so kind. You're welcome. And then I'll do one more for you because of poor Camden. I mean, he's not here right now. Poor guy. I'll do this one. 142. F of y, sine of pi over y over tan of pi over y at y equal to 1. And the directions are asking you, decide if the function is continuous at this point. And if it's not, tell me what. Is it continuous? So again, depending on how you look at this, here's what I would do. This one I would do actually slightly differently. I would do what we know tan to be. What's tan equivalent to? You all know that one. Sine over cosine. So if I do this and I say sine of pi over y equals sine of pi over y over cosine of pi over y. Y'all agree, right? All right. Now, before we get there, the problem I have is when this is equal to 0, when this equals 0, right? Or when this guy equals 0. That's where I have problems. Do you agree? When that is equal to 0. Because I don't want the bottom to be equal to 0. So again, we're going to have issues at the asymptotes because we're talking about tan again, tan of pi over y. So what you can do is you can actually plug this into your calculator in radians. You can do the crossing off. Let's do it that way. Times same change flip. Correct? These are going to cross off. So what does that mean? When you cancel out, you are a whole. You are a whole at y equal to 1. Whole, another name for whole is removable. So that's what they're going to ask you on the homework tonight. So that's all they're asking for. They're like, at 1, at the point 1, are you continuous there? No, you have a hole right there. It cancels. You could have checked it on the calculator. You can put it in your calculator. Make sure, I'm writing all different ways to do this because I'm nervous for you. Make sure it's in radians. And you could do like, 0.98, 0.99, 1, 1.01, 1.02, and look to see what you're approaching. And you'll actually see there's an error right here. There's a hole right there in the graph. So just 2 ways to do those one. All right, that's it. I just did 2 of your homework. You're welcome. 2.4, number 131 to 144. And 2 of them are done. 30 minutes of a lecture. Will Cam